Hi. I I want to give you an overview of z-scores and how to make sense of them. This is originally a PowerPoint with audio, but I understand that causes problems for some folks, so I'm going to try and redo this morning as a PowerPoint video. I want to talk about z-scores and how to make sense of z-scores, which is this week's chapter, which is about continuous probability distribution, because z-scores are based on a continuous probability distribution. I mean, last chapter we talked about discrete probability distributions, which are based on discrete numbers. Continuous probability distributions are based on continuous numbers, as it seems reasonable and logical that they might be. This upper chart up here is a discrete probability distribution. It has three discrete points, 1, 2, and 3, and then probabilities associated with those things. Down the bottom down here, you've got a curve, however, and that's what's more what continuous probability distributions tend to look like, because in the discrete probability distribution, there's no point between 1 and 2. I mean, you either have a 1 or a 2 or a 3. Those are the only three choices there are. In a continuous probability distribution, you could have 1 or 1.5 or 1.75 or 1.93, or all the different points between 1 and 2 are possible in a continuous probability distribution. That's the kind of key difference. Discrete probability distributions, the simplest case of those is a binomial distribution. And you had some stuff in that last week where it's a simple yes or no. More commonly where there are 4 or 5 possible choices for a distribution. There's no simple case with continuous probability distributions. There's just a bunch of cases in it, and that's kind of a basic point of it. With a continuous probability distribution, the kinds of questions we might be looking at are things like, what is the likelihood on a given day that a minimum lowest temperature might be above freezing? That and mathematically, what they're talking about here is the minimum temperature of a day is greater than 32. The lowest temperature of the day is bigger than freezing. And again, on temperature is one of those continuous variables in which there are an infinite number of gradations depending on the sensitivity of your measuring device. Temperature is a really good continuous variable around that kind of stuff. And what we're looking at here is what's the probability of a temperature being greater than 32 on a given day. The way we answer a question like that is we look at historical data for what minimum temperatures have been on this specific day. Now this is a graph of what something like that might look like, where, for instance, for the given day we're talking about, the average temperature might be 45, which is, and the standard deviation might be 13 degrees. Those are, I'm going to point out for you, those are measurements that you've heard over and over again so far, what the average is and what the standard deviation is. That's coming up again, and here's a place where that's going to come back big time for us. The percent of cases to the right of the blue line right here is the probability of the minimum temperature being more than 32. The height of the distribution is the probability, the height of the line where this blue line crosses it tells you, that gives you a sense of what the probability is on that given day. Now it's important to remember a couple things here. Let me go back. This is a probability distribution, and because of that, the area under the curve here is equal to 1, because if you add all the probabilities coming up for under a continuous probability distribution, it cannot be more than 1. 1 means that's all the possibilities. So everything under the line here is the area under this line is equal to 1. So that's a z-score. Mathematically, z-scores are really simple. You take the raw score, whatever distribution you have, you subtract the mean of that thing, that distribution, and you divide by the standard deviation. Mathematically very simple. A subtraction and a division. You know, it's something you can do. It's not hard to find z-scores. In this case, a raw score of 32, the mean is 45, the standard deviation is 13. So 32 minus 45 divided by 13 is a -1. Now, z-scores can be positive or negative. If you get a z-score of 0, what that really means is the point you're talking about, the raw score, is the same as the mean. So if I had a raw score of 45 and I subtract the mean from that, which is 45, I would get 0. The mean of a standard distribution is 0. The center point of it tends to be 0. 50% of the scores are higher than that. 50% of the scores are lower than that. A z-score is a standardized normal score. It's a way of transferring or transforming raw scores into something that allows you to compare them to other things. What do I mean by that? Suppose I want to compare 32 degrees on the day I have in mind here, where the average temperature is 45 and standard deviation of 13, with a day 13 or 14 days later. Well, scores, things are different. Z-scores allow me to compare things between different kinds of distributions, and that's a really useful thing. For instance, here are 4 different distributions. This one here, the blue one, is narrow and high, small standard deviation, big mean. This brown one down here would say to me a big standard deviation. It's the standard deviation is really spread out, but the mean is not much bigger than anything else in the area. The green one has it's a much lower, as a smaller standard deviation. The red one has probably the same, or has a lower mean. The red one has probably the same mean as the blue one, but the standard deviation is different. Different distributions look different. They can all be changed into z-scores, and you can get comparability. Now there's a Excel formula that looks like this, for instance. Again, you don't need to do this Excel formula for most of this Excel function for most z-scores, because it's fairly straightforward. What I've done here, but there is one called standardize, and what you do is you put in your raw score, X, in this case 4, your mean, which is 3, and your standard deviation of 0.5, and what it does, it kicks out for you is the standard deviation is 2. Think about that again. What I've said was the formula is the raw score minus the mean divided by the standard deviation. The raw score of 4, mean is 3, 4 minus 3 is 1, divided by the standard deviation, which is 0.5, gives you 2. Now again, this is fairly straightforward. But if I'm giving you a mean of 7.358 with a standard deviation of 0.6653, a formula like this, the standardized function, becomes much more useful in that case, because you could probably do the math in it. It's not terribly hard math, but doing this makes sure that you don't make any arithmetic mistakes. That's the big value of the standardized function within Excel. A standardized normal distribution has probabilities associated with every z-score. Every z-score has a probability associated with it. And that has been, those things have been worked out mathematically. I'm going to say, trust me on this. They will tell you the probability associated with that z-score. And here's one of them, again, a normal curve, and z-scores plus or minus one z-score and a normal distribution has 68%. Just more than 2/3 of all scores will fall between plus and minus one standard deviation. 95% of z-scores will fall between +2 and -2 in a normal distribution. 99.7 of them will fall between +3 and -3. That you know where these lines fall and what percent fall in each area here tells you some things. I mean, for instance, if you have a z-score of 0, then what that tells you is 34 plus 14 plus 2. And that comes out to be what? 58, 48, 50%. 50% are less than 0, 50% are more than 0. If I say I have a z-score of -1, what I know is 16%, 14 plus 2, is less than -1. If I have a z-score of +1, what I know is 50%, that's this middle piece here, plus 34, that's this area in here, fall to the left of it. So 84% of all scores will fall less than +1 z-score. This is the value, particularly of being able to change raw scores into z-scores. If you take a test and the mean on this test is 93 and you get with a standard deviation of 10 and you get 99, for instance, as your score, is that a good score? Well, yeah, it's bigger than mean, so I guess it's a good score. But by changing those things into z-scores, you can tell exactly how you did compared to everybody else who took that test. It's a really nice way of sort of making sense of allowing you to put a raw score into perspective in terms of overall scores. So going back to the temperature problem, what I'm interested in, the temperature problem is, again, the problem is what's the likelihood that a temperature will be above freezing on a given day when the mean for that day is 45 and the standard deviation is 13 on that day. To get a z-score, it's 45 minus 32 divided by 13, and that comes up with -1. That means it happens to fall right here. Gosh, oh golly, isn't that neat how that worked out? It's easy when you construct the problems in your head. What that means is 50% are greater than 0, 34% are between -1 and 0. So you got 84% of the time, the temperature will be greater, the minimum temperature will be greater than 32. That's the probability. Doesn't mean that's going to be that way today. What it means is the probability that the temperature on that day, when the mean is 45 and the standard deviation is 13, 84% of the time, the temperature is going to fall above freezing, the minimum temperature. I say, why would you want to know that, Steve? It's like, well, you want to plant, do you want to put stuff in the ground yet? That would give you a sense of what's the probability you're going to get a frost. It's a way of getting some information to allow you to make better decisions. That's what I just said. See here. Here's a little bit tougher problem. What's the probability of getting a temperature between 32 and 58? That is between and 58 is 58 minus 45 is 13, divided by 13 is a 1. So what's the probability the temperatures will fall between a +1 and a -1, between 32 degrees and 58 for this day? Is 68%. but roughly 2/3 of the time it'll fall, the minimum temperature will fall in that range right there. Again, here's the math of that. 45 minus 45, what I did here is well, this is a different problem. What's the probability of a specific daily temperature between 45 and 64? Well, 45 minus 45 is 0 divided by 13. So that's me a z-score of 0. 64 minus 45 divided by 13 gives you a 1.46. So you're asking, what's the probability the temperature, the z-score of that temperature will be between 0 and positive 1.46? Visually, it looks like this. What's the probability that the temperature will fall in this darked out range here? And I gotta tell you, I wish I had the precision to be able to come at this and get exactly to 1.46, but it comes out closer to 1.5 if you look at my drawing. That's my incompetence as an artist as opposed to the mathematics of it. But that's the area you're trying to figure out. What's that area? Because that's the probability then of that the area under the curve between 0 and positive 1.46 z-score is the probability the temperature will fall in the range I mentioned. Well, there's a couple ways you do this one. And again, I'll come back to, there's a formula in Excel called norm.dist, D-I-S-T, the normal distribution. And what I put into this is I put in 45 for the raw score, 45 for the mean score, standard deviation of 13, true, which means cumulative, you remember that, and it gives me a 0.5. I've been telling you that all along, so that shouldn't be a surprise for you that comes up 0.5. And then I come down here and I say, let's put in 64 as the raw score, 45 is the mean, 13 is the standard deviation, true again, and it tells me 92.8%, 0.928% of the cases fall to the left of that point. Now let me go back one. What I've just done is I said, what percent fall to the left of 0, which is here, and that's 50%. What percent fall to the left of 1.46, which is this point? Now that would be everything all the way across here. So what I do is I take the percent that's to the left of this point, that means everything, and then I subtract the percent which is left of this point, which is 0.5. So what I'm going to do is I'm going to take 9.928 and subtract 0.5. And it says to me 42%. Well, it could be 928, it could be 9.3, so this could be a 40.43. So roughly, rounding, 40.43 would probably be a more accurate number here. But that's how you would find this area here in the process. Remember, it's important to remember that the area under the total curve is equal to 1. That's the probability. So you can always work with things in relation to that 1. It's a really useful thing to keep in mind here. This came up in the last week when we talked about discrete probability distributions, the difference between true and false. True means the cumulative probability, the probability of something up to and including that point. No matter where it's at. The Excel formulas will not let you figure out directly the percent to the right of that point. It always tells you to the point to the left of that point. However, you could put the alternative to it is instead of putting true in here, it's put in false. And then it doesn't give you cumulative, it tells you the probability of getting exactly that point. What's the probability of getting a specific point? The true-false language is confusing, and I'm sorry, but it's how Excel does it. I can't change Excel around for you here. But true speaks to cumulative probability all the time. False speaks to point probability, the probability of getting a specific point on that curve. What you're going to be doing this week particularly is you're going to be converting raw scores to z-scores. One of the things I'd encourage you in that process at some points is, because I'm going to give you some fairly complex problems with this to think through about it. Draw yourself a rough standardized distribution and try and figure out what is exactly you want to know. What's being asked of you in the process. That's really helpful, I think, to be clear about what exactly is Steve asking for here. And remember that norm.this with true tells you the probability of that score or less. And you may add or subtract things based off that. That's an introduction to z-scores and how to use z-scores. Z-scores are really useful. If you want to know how you're doing in relation to some different groups, and well, for instance, let me give you a couple of examples here. I've taken different IQ tests, and I did it in part because I was, as an undergraduate, I was in a program with a bunch of students, and they had to administer tests, and so they were always looking for somebody they could administer a test to. And being a guy who was really interested in test theory, I kind of went, well, I'll take it. You got a test, I'll take your test for you. And I joke about the fact that my favorite IQ score is the Raven's matrices, because it's the one I score highest on, and therefore it must be the best assessment of intelligence. Truthfully, there are different kinds of intelligence, and different tests measure different kinds of intelligence. But you take two different IQ tests, and on test number one, the mean of the test is 105 and you score 120, and I did pretty good on this one, and the standard deviation is 10. And you take another test, and the mean of that one is a 100 and you score 125 on that one, but the standard deviation is 15. Which one did you do better on? Well, you're tempted to say, well, if I scored 125 on this one, 120 on this one, I must have scored, the 125 might have been the better score. Maybe, maybe not. Whether or not your 125 is a better score than 120 depends on what's the mean of the two distributions and what's the standard deviation of them. And that's the changing all those things into z-scores tells you exactly that information. And it can also tell you, for instance, if you score 2 standard deviations above the mean, it can tell you what percent of the people you scored better than on your IQ test, which is interesting information. It doesn't get you a free cup of coffee or anything like that, but it's interesting information to give you perspective on how well you're actually doing. If you have exams and different courses, and on one of the exams you score a 72 and the other score you not score a 93, it's like you're tempted to say, well, the 93 is a better score. You know, I did much better in this one. And the answer, my reaction is maybe. You scored more points on it. Is that mean you did better? What's the mean? What's the standard deviation of the two different test groups? And how you do in relation, if you get z-scores for both of them, because if you find out the means and standard deviations of the outcomes, you could tell how well you did compared to the rest of the group. And it could turn out that the 73 is actually much, you know, if you got a 73, but the mean of the group was 50 with a standard deviation of 15, you did really well. You did better 2 standard deviations of the mean for that one. Whereas if you got a 92, but the mean of the group is 90, a standard deviation of 5, you didn't do bad, but you did better with the 73 than you did with the 92. So it's a way of taking these raw scores and change them into something that are comparable across groups. And that's what we're trying to do. And the neat thing about a Z-scores, because it also, not only does it tell you how you did in relation to other people, it tells you what percent of the group you scored larger than. You can figure that out. What's the likelihood of doing that well for people generally? And that's really interesting information. It informs what you're getting against a much larger context. And that's the value of these scores. That's why I want you to learn how to use them. And that's a place where continuous probability distributions get into its real power. I hope you enjoyed this week.